Hi, and welcome to H1.3, the equations of rotational kinematics. In this lesson, students will be able to use rotational kinematic equations to solve for various physical quantities. Way back in Unit 2, we derived some useful equations for the kinematics unit. Let's translate those linear kinematic equations into rotational kinematic equations. And take a look, I even color coordinate all of these. They're going to magically change colors. Wow, very nice. So we have like a blue acceleration, a blue angular acceleration, right? What is this, orange or yellow? Final velocity, orange or yellow? Final angular velocity. So we're going to get some practice with these Greek letters here. So the first equation, oh, and by the way, I should say like these are the base equations, like the definition of the average velocity. And this is the definition of what the acceleration is. So we're just describing your change in displacement over time. That's your velocity. Your change in velocity over time, that's your acceleration. And then to calculate the average velocity, we said just take your final and your initial and divide it by 2. That's taking the average of two numbers. So we took those base equations and derived a few more. So do you remember what the equation without d in it is? It's this one. It's just a rearranging of this formula here. We solved for VF. Then try to figure out, if you want, you could write it down on your own. Try to like translate each one of these terms into its rotation version. So instead of a VF, you would write omega F, and so on. So practice it first. Pause the video, and hopefully you had something that looks like this. Omega F equals omega I plus alpha T. Then we derived an equation without the acceleration in it. Looked like this. It's the secret formula. It's just a combination of this one and this one together. Okay? So what is the equivalent of this formula with rotation variables? So again, pause the video and try to rewrite this formula with rotation. So the formula without alpha is theta is equal to 1/2 times omega F plus omega I times T. All right, then we derived an equation without the final velocity. So which equation doesn't have final velocity? That's this one, d equals VIT plus 1/2 AT squared. Again, pause the video and see if you could translate that into your rotation variables. So without omega F, we have theta is equal to omega IT plus 1/2 alpha T squared. And then the equation without T in it looks like this. VF squared equals VI squared plus 2AD. Again, please pause the video and see if you could rewrite this. Practice writing and understanding these weird Greek letters, right? So that's like basically the new thing for this unit is now we're using Greek letters instead. One of the new things. So hopefully you pause the video. We have omega F squared equals omega I squared plus 2 alpha theta. Very cool stuff, right? Because d is equal to theta. Okay, very nice. So luckily, I give these to you in the new reference table, page 7. And they're all located right here. Oh, except I didn't give you the secret formula. Let's see if I could rewrite it myself. Oh, man, I'm going to have to remake this, I guess. Let's see. I knew I was missing something. The secret formula. That's D is equal to 1/2 VF plus VI times T. Really, it's theta is equal to 1/2 omega F plus omega I times T. So that is a kinematic equation, the secret formula. It's not given to you on the New York State Physics reference table, and I forgot to give it to you over here. Maybe I'll edit this one day. But yeah, that's kind of nice. So you might want to write that in. And yeah, those are the formulas. Beautiful. So now we can use these the way we used the other kinematic equations. The other thing I was going to point out before I realized I forgot to write this one in there was that the units must agree. So if you had theta in terms of maybe it's revolutions instead of radians, or degrees instead of radians, then your omega I would have to be in revolutions per second or degrees per second, and alpha would have to be in revolutions per second squared and degrees per second squared. Everything has to agree. And then for these formulas down here, you need to use radians for everything. Cool. So let's see if we understand that. All right, this is like a check your understanding question. It says the equation theta equals omega it plus 1/2 alpha t squared is being used to solve the problem in rotational kinematics. Which one of the following sets of values for the variables omega I, alpha, and t cannot be substituted directly into this equation to calculate a value for theta? Which one of these can you not use? Which is not currently ready to be plugged in to that equation? You could pause the video and think about it. Well, I'm looking at radians, radians. Okay, that's looking good. I'm looking at revolutions, and this is radians. Those do not agree. I'm going to have to, I'll probably convert this into radians per second before I do anything else. Now, this is revolutions per second squared, and these are all just seconds, so that's, that's fine. So yeah, if it's revolutions and revolutions, that's good to go as well. You could plug those right into a kinematic equation, those equations on top that we just saw, and that's totally fine. So you cannot do B. All right, you'd have to convert some units first. So let's put this into practice. We got a nice word problem here, and we're going to do the guess method. Feel free to pause the video, read it on your own, and try it. But I'll do it right now. It says, the blades of an electric blender are whirling with an angular velocity of positive 375 rads per second while the puree button is pushed in. When the blend button is pressed, the blades accelerate and reach a greater velocity after the blades have rotated through an angular displacement of positive 44 radians. The angular acceleration has a constant value of positive 1,740 radians per second squared. They want you to find the angular velocity, the final angular velocity of the blades, and how much time does it take to undergo this angular acceleration. Great. Hopefully, like you, this is pointing out to me first. It's not going to really affect anything, but just so we know, if it's positive, is that clockwise or counterclockwise? Positive is going to be counterclockwise. Okay, just so we know. It doesn't look like we're slowing down or anything, so we're not going to have to plug in a negative number since we're speeding up. That means not only is your initial angular velocity positive, but since you're speeding up, we know we're going to get, and they tell you, this is positive as well. So it's all good. And then we know we're going to get a greater final velocity in the positive direction. All right, let's do the guess method. So the first thing that sticks out to me is the initial angular velocity, omega I, is equal to 375 radians per second. Then the angular displacement, theta, is positive 44 radians. Oh, they were nice. Maybe I could have made this in revolutions and been like a little trick. You'd have to convert that into radians first, or even this in revolutions per second. But they're all in radians, so that's good. Like the angular acceleration, alpha, is equal to positive 1,740 radians per second squared. The first part A looks for the final angular velocity. So we are looking for an equation in our list that does not have t in it. If we see an equation with t, we don't want it. So you could pause the video here, and maybe this is, if you were stuck, maybe this is a good clue. Which equation would you use that doesn't have t? I would use omega f squared is equal to omega I squared plus 2 alpha theta, 2AD, right? Vf squared equals Vi squared plus 2AD. Well, we could say omega f squared equals omega I squared plus 2 alpha theta. So then you plug in 375 squared. Oh, my bad. That is the final. Oh, man, how embarrassing. That's okay. So we're looking for the final angular velocity. The initial angular velocity is 375. 2 times alpha, which is positive 1,740. And it goes through an angular displacement of 44 radians. Man, that was really nice that everything was in radians. You didn't have to convert anything. I wonder if they'll get harder. Keep an eye out for that. And then you take the square root, and you should get positive 542. Okay, what are the units for your final angular velocity? Hopefully you're saying it's a radian per second. Very good. Okay, so a couple things that could have made this harder was maybe they're not all positive. Maybe they say, oh, this is clockwise and the other one's counterclockwise. Then you'd have to know, you'd have to be careful with your sign over here. All right, remember, clockwise is negative, counterclockwise is positive. So you got to be careful with that. Luckily, everything was in the same direction, so that didn't come up. And then what else? Oh, there's a whole other part B, which I'll do. But another trick that they could have done, like we said, maybe this isn't a revolution per second squared, or they tell you it rotates 5 times before it completes the acceleration. You'd have to make sure your units agreed. It doesn't necessarily have to be in radians, as we discussed, if you're just using a kinematic equation, but they have to agree, so keep an eye out for that. All right, part B asks how much time does it take to do that acceleration. So yeah, we do know the final angular velocity now, but we rounded that answer, so I'm going to try to find an equation that does not have omega f in it, which is the one that's kind of like d equals vit plus 1/2 at squared. And now I'm second guessing my approach. The d is equal to v omega I t plus 1/2 a alpha t squared, right? I'm saying like both linear and rotation at the same time. Why am I second guessing myself here? Because omega I is not 0, and if we're solving for the time, this is going to turn into a quadratic formula. And even though this is a rounded answer, I could live with that if I could get away with not doing the quadratic formula, which I recommend you do as well. Listen, if you like the quadratic formula, that's totally fine. But let's use an equation that does have omega f in it, just something to solve for t. So which is my go-to equation if I have a choice? Normally it would be vf equals vi plus at, but instead we'll do omega f equals omega I plus alpha t. All right, no squaring necessary, no quadratic formula, nothing crazy like that. We do have the disadvantage of having a rounded answer here, but you know what? That's fine. It's still going to be like a good answer. So this is 1,740 times t. So you do the subtraction, and then you divide, and you get a time of, it's a very short amount of time, 0.0 Oh, my bad. Well, I'll just write it in scientific notation. It's be 9.597, so 60 times 10 to the negative 2 seconds. I was about to write it like this: 0.096 seconds, right? So a very short amount of time to go from that puree function to the blend function, which is what we want. We don't want a big lag time for it to accelerate. We got food to make here. Looks like they're making a nice smoothie in that blender. All right. Hey, beautiful. It's like a 15-minute lesson here. Let's do some practice problems. Thanks for watching and have a great day.